Hello everyone. Today let's go over another medium question that I just solved by myself. This one is called most beautiful item for each query. So you're given an input array where it's a 2D array of integers, the 0th index being the price and the first index being the beauty. And you're given another integer array that's a 1D array called queries, and you want to determine the maximum beauty, which is going to be the 1th index, if you recall, of an item whose price is less than or equal to queries j. If this is not possible, then the answer is going to be 0. So essentially what this is saying is that you want to find the biggest value for the number that's less than or equal to but closest to this particular number. So for example here, I think 4 is a good example to use. So we have keys 1, 3, 2, and 5. For 4, we're going to use 3, not 5, because 4 is not in items as a key. And also 3 is less than or equal to 4 and is also the closest to 4. So in that case, the answer for 4 would be the biggest for 3, which happens to be 5. So that's why for index 0, 1, 2, 3, 4 is 5. So this is a classic binary search question. You can solve it using double loops, going through every single element, trying to find the optimal partition point, but binary search is much more efficient, so I'm going to go ahead and show you the way to do it. First, let's create a hash map. This is going to hold it's going to map the 0th index to the first index. Let's go ahead and do that. Let's print this out. So cool. Now what we want to do is get the biggest. So we only care about the maximum beauty, right? So the values of each key are the possible beauties, and we also want to keep track of the historical biggest beauties, right? So for example, this is not a good example, but if 2 were 6 and then 3 were 2, 5, obviously even though the key is smaller, it has a bigger historical beauty, so you'd still want the historical beauty at time 3 to be 6. So we want to create a variable called current, and first let's sort the dictionary by the keys. And let's print it out. Okay, so now they're sorted by their keys. We can do this, tracking the biggest historical beauty seen so far. So current equals to max of current, and a better way to do this instead of appending, because we want these to be sorted, it just happens to be so, doesn't mean it always will be, is by using a heap. 0, I1, so it's going to be in ascending order. Let's see, this looks the same. Okay, cool. So now we can simply go through, and because we already sorted these by using heaps to push them in ascending order, we know that the last one is always going to be the biggest one, right? So current equals to max of current, dk, -1, right? The last index value. And let's print the current out to C. And let's also print k out, because we can treat k almost as like the time and the biggest beauty seen so far up to this time. Let's create another dictionary and let's map it. So my D, we don't even have to create a default list this time because this is a one-on-one mapping from the current price and the biggest historical beauty possible up to this point. So let's say my D of K equals the current, and let's print the dict out to see. Okay, awesome. So now that we have this, we are ready to do our binary search. So the question next says that we want to find the biggest beauty for whatever price is closest but not bigger than the current query. So let's iterate over this query first, and let's create another. We want to binary search over the keys of this dictionary, right? So let's create a list of the keys and also sort them, because binary search only works if you have a sorted list, right? Because how else are we going to throw away half? So 1, 2, 3, 5 are the keys of our dictionary. Now we're ready to run our binary search. And binary search works by starting at the first and the last element and splitting, kind of a divide and conquer technique. So we don't want to miss any elements. That's why I'm using equals. Usually that might be an edge case. Okay, we're finding the midpoint, right? And then if A of mid, because that's the current value we care about, is equal to query, then, right, so let's create an array called possible. So possible.append A of mid, because that's going to be one of the possible values that we want from the historical moment, right? That might be the biggest one. Because these, again, 3 could be 2, 2 could be 4. This just so happens to be. So we're going to append that, and then we're just going to keep doing our binary search. If that's not the case, if we're way too big, then obviously right equals to mid minus 1. Else, if we're too small, again, smaller might be a bigger historical value, so we actually want to, just in case, append A of mid before, moving, throwing away the left half of the array. And now we can print possible. Let's see. Memory limit exceeded. Okay. Okay, that's strange. Maybe we need a set. Let's print this out to see. This is still memory limit exceeded. That's strange. Let's refresh this. Is that probably why? Nope. Let's get rid of this. Let's see what's going on here. So Q and A. Okay, so that's fine. Except now, how do we do the binary search, right? Now, again, these are indices, right? And then if A of mid is equal to Q, again, that's fine. print a mid. If a mid is too big, then we throw away the right half. Else, we also, because that still satisfies the rule of being less than or equal to. That's strange. Output limit exceeded. Is there an infinite loop somewhere here? Perhaps. Okay. All right. Because just because we found the midpoint doesn't mean that we have to doesn't mean that we're not going to move the pointer, right? Okay, so possible. So, okay, let's just do this now. Don't need this. 2, 2, 3, that's not right. That's not what we want. Some missing issues. Okay, now because, okay, we were missing results. Now we have 1, 2. Okay, awesome. So now, cool. So now we have all the things that we need. Let's call this, declare an array called answer because that's what we want to return. And then now that we got this, now we can just map it to the values, right? Because that's what we need. And we know the last one is going to be the biggest one because of how we arrange this binary search. And because of, yeah, because of the binary search. So now let's, if not possible, as the instructions say, then answer.append 0. If possible, then answer.append myd possible -1, right? Because that's the biggest one is going to be whatever the key or the value is. Print our answer out. As you can see, right? And there you go. So, yep, just some edge cases there, but it shows you the power of binary search. And again, just to recap, sort the values of each key of the dictionary, sort the dictionary by the keys, keep track of the historical beauty for each of the keys in ascending order, sort the keys, create a list for them, go over the queries, run a binary search to find the optimal partition point where you're not going to be bigger than, but you're closest to the current Q value, and then simply append whatever closest value you found, that value, the biggest value of that, which we already got rid of the other non-possible ones because of the way we did this mapping in the dictionary. And then if that's not it, if there's not any possible values, then just append 0 and then return the resulting array at the end. So yep, that's it. I hope this is helpful and stay tuned for more. Thank you for watching.